Okay, so we have now gone on to the final chapter of Further Mechanics 2. It's a very short module here, and it is dynamics. And really, there's not a ton of new stuff here either. It's kind of just building on all of the things that we've done in Core Pure and all of the things we've been doing so far in Further Mechanics 2 and Further Mechanics 1. So it's called dynamics, and dynamics is the study of forces and how they produce movement. And simple harmonic motion is going to be the bulk of this chapter. Obviously, exercises A and B, they kind of follow on really directly from chapter 4, which is kinematics with calculus. And then 5C, 5D, and 5E are all to do with simple harmonic motion. And just to kind of introduce simple harmonic motion, in case you haven't come across it before when you've been doing Core Pure, these are 3 different examples of simple harmonic motion. So here we've got like a particle that's at the end of a spring, and it bounces down and it bounces up again. So it's kind of going down and up, down and up, down and up. That's something that we called simple harmonic motion, or SHM. We've also got a little child that's swinging on some swings here. This is like a representation of a pendulum, of something that is going back and forth. That is something that is also an example of simple harmonic motion, of something that is just kind of going back and forth like this. I think when we've looked at it in Core Pure, we talk about damped harmonic motion, where it will eventually kind of slow down and come to a stop. We're just looking at simple harmonic motion in this particular part. And then I've also got the way that the tides will move. When you have high tide and low tide, they can also be modelled by simple harmonic motion. And this is kind of the giveaway that simple harmonic motion is stuff to do with like sine and cosine. It's to do with that kind of trigonometric patterns. But we're going to pause on that because the first couple of exercises, like I said, are a direct run-on from Chapter 4's kinematics. So we're going to look at some equations of motion. And when I say equation of motion, I'm normally just talking about F equals ma. So we're going to look at some equations of motion here and how we can use calculus. Now, previously, we could only apply F equals ma to situations where the forces were constant. Now, with calculus, we can solve problems where the forces are variable. And this is actually really useful because lots of forces are going to be variable, like things like air resistance. Loads of things are going to vary about how fast something is going or what position it might be in. And like I've said before, this directly follows on from Chapter 4's kinematics. So we have these 3 different versions for acceleration. We have that acceleration is the second derivative of time, the second derivative of x, with respect to time. We don't really use this one very much. You'll find it's basically going to be one of these 2. And you would select this for the acceleration if the question was going to be in terms of x and t. Maybe it's to do with distance and time. If the question is wanting stuff to do with v and t, we would probably say that acceleration is dv dt. And if the question is in terms of the speed and displacement, we would use that a is v dv dx, which sometimes we used as the ddx of a half v squared. To be honest, these are just the 2 that I remember, and I think which of these that I'm going to use. Now, I wanted to add in something that's not in the textbook, but is still very useful to think about. If they ask you to work out the work done by a variable force, we can just adapt our formula. So we know that the work done is normally the force multiplied by the distance, but that's only if the force is constant. If this thing is varying, we have to just change the formula so that the work done is the force times by the distance, and you sum up all of those things. So it's the same thing, force times distance, f dx, and summing that up so that we come up with the overall work done. And then for the impulse, if you do ever have a question about impulse, which I haven't seen yet, but I just kind of wanted to mention it as well, impulse is normally force times time. So with a variable force, you would integrate the force with respect to time, and that would tell you the impulse that was done across a particular time period. Obviously, these limits here would be with respect to time, so they would be time limits, and these limits that would be here would be to do with the distance that it's moved. So if it was how much work was done in the first 3 meters, you would do 0 and 3 in that particular case. And I'll show you an application of that later on where it pops up, and I can also show you it with a different consideration with some energy. So I'm going to do 1, 2, 3 examples, and then you're going to pause the video and have a go at that one about a car that we've got there. So a pebble of mass 0.2 kilograms, and I'm always going to jot down the things that I think are going to be useful in the question, of 0.2 kilograms is moving on a smooth horizontal sheet of ice. At time t seconds where t is greater than 0, a horizontal force of magnitude 2t squared newtons and constant direction acts on the pebble. When t equals 0, the pebble is moving in the same direction as the force and has speed 6 meters per second. So when t is equal to 0, the speed is equal to a positive 6 because it's going in the same direction. And when t is equal to capital T, the pebble has speed 36. Now, it's a very, very boring force diagram we've got here. There's no friction or anything. There is just a horizontal force of magnitude 2t squared that is acting on this pebble at this point. And so we're going to do an equation of motion for this that we've got here. We're going to try and find out what that value of t is as well. Now, it's just worth thinking about here that to begin with, there is no force that's being added. As t increases, the force is going to be increasing as well, because obviously you're going to take that time and it's going to square and it's going to add to and multiply by 2. So we're interested in stuff to do with v and t. Obviously, the clue here is that we've got a mass and a force. We know we're going to be wanting to do an equation of motion. And so the value of a, or not the value of a, but the version of a, because we're interested in v and t, we're going to use that a is dv dt. So I'm going to start off by doing f equals ma, and obviously the direction I'm going to use that's positive is going to be to the right. So that's 2t squared equals the mass, which is 0.2, multiplied by the acceleration, which is dv dt. And here we have a differential equation, which is really the theme of what all of chapter 4 was about. So I'm just going to integrate this. I'm going to put the dt onto this side, so I get 2d squared dt is equal to the integral of 0.2 dv. Integrating this, I'm going to increase the power, divide by that new power. I'm going to integrate on this side, I get 0.2v plus c. Now I need to find out what that c is, but they told us this, that when t is 0, v is 6. So when t is 0, v is 6. So 0 equals 0.2 multiplied by 6 plus c, which means that c is equal to minus 1.2. So I'm just going to take this equation and put it up here. So I get that 2/3 t cubed equals 0.2v minus 1.2. And now I'm going to try and find out what t is equal to. So v is equal to 36, and little t is equal to capital T. So that's 2/3 t cubed equals 0.2 times 36 minus 1.2. So I'm just, on my calculator, I'm doing 0.2 times 36, I'm subtracting 1.2, I'll times it by 3 and divide it by 2, so that I get t cubed is equal to 9, and I'll just do the cube root of 9, so I would do 9 to the power of a third, because I can never find the cube root button, and I get that t is 2.08 seconds, and that is obviously to 3 significant figures. 2 or 3 significant figures should always be the thing that we're looking for when we're doing these kinds of things. So it should feel pretty familiar. It should just feel like some of the normal stuff that we've been doing here of just setting up an equation. And this time it's just that we have to be careful of those forces to begin with. Okay, let's look at this next one. It says a particle P of mass 1.5 kilograms is moving along a straight line. The force acting on P has magnitude 8 minus 2 cos x, where x meters is the distance OP, and it acts in the direction OP, which literally just means it is acting away from it like this. Because if you imagine we have O, we have the particle over here, the force is acting in that direction, OP. Okay, so the force is 8 minus 2 cos x. And what else have we got here? We said when P passes through O, when it passes through O, in other words, the displacement is 0, the speed is 4. And we're going to try and find out later on what is the speed of P when x equals 2. So we're going to say when x equals 2, what is the speed equal to? Well, obviously we're going to do F equals ma. But this time, you'll notice that we've got x and v. So the value that or the version I'm going to use for x, I said value last time, I mean the version I'm going to use for a instead of x is going to be v dv dx. The reason I'm doing v dv dx is, of course, because I have x and v. That's the stuff I'm interested in, and I have x and v in that one. So doing F equals ma, I get 8 minus 2 cos x equals 1.5 v dv dx. And then I'm just going to solve this, okay? So I'm going to multiply up by that dx so that I get the integral of 8 minus 2 cos x dx equals the integral of 1.5 v dv. So integrating on this side, I get 8x. Sine differentiates to cos, so cos is going to go to minus 2 sine x. And then 1.5 v squared, I'm going to have that as 1.5, not 1.5v squared, 1.5v. I'm going to increase the power and divide by that new power and have that constant, which is c. Now I'm going to use this information, which is that when x is equal to 0, v is equal to 4, and that will hopefully tell me what c is equal to. So the left-hand side is just 0 minus 0. I then get 1.5 divided by 2 multiplied by 4 squared plus c. So c is going to be the negative version of that. So 1.5 divided by 2 times 4 squared, which means that c is negative 12. So I'm going to take this equation, which is 8x minus 2 sine x, and that is going to be equal to 1.5 divided by 2, that's 3/4. That is 3/4 v squared minus 12. Now we're trying to find out the speed of p when x equals 2. So x equals 2, I'm going to find out what v is equal to. So it's going to be 8 times 2 minus 2 sine 2. I'm going to add on the 12, and that's equal to 3/4 v squared. Now obviously, because we're doing everything to do with calculus, we do need to make sure that we are in radians mode here, just as a reminder for that. So I'm going to do on my calculator 8 times 2, so that's 16 minus 2 sine 2 plus 12. I'll times it by 4. I'll divide it by 3, so that I've got v squared is 34.9. And when I take the square root of that, I'm going to say to three significant figures, 5.91 meters per second for that one. So I've got 5.91 meters per second. Now, for part B of this question, it says find the work done by the force in moving P from x equals 0 to x equals 2. So we're going to use either energy considerations or we're going to use the integration one. So I'm going to do both of these. Hopefully I'll be able to fit them on this page. If not, I can always add in an extra one. So I'm going to integrate the force, which is 8 minus 2 cos x with respect to x. And remember I said the limits here have to be where it starts and where it finishes as a distance. And it's moving from its initial position as 0 to the final position of 2. So it's moving between 0 and 2. Now I've already actually done that integration. I did it over there and it was 8x minus 2 sine x. And that's just going to be between 0 and 2. So when I sub in 2, that's going to be 8 times 2 minus 2 sine 2. And when I sub in 0, it's just going to be a 0, so I don't need to bother with that. So that is 16 minus 2 sine 2, and that is going to be 14.2 joules. Of course, all my answers are to three significant figures. Now, if I was going to do it in a different way, we're going to think about it as the energy considerations. Now, this is the work done by the force. So to begin with, we would say that it has the kinetic energy, and to end with, it has higher kinetic energy. So I'm going to say that the initial kinetic energy is going to be equal to the final kinetic energy, but in order to increase that kinetic energy, the work is doing a force. Normally, we would say work done against friction on this side. The work done by the force, or the work done by the engine, as I've sometimes referred to it in the past, will go on this side. So I'm going to put the work done. So this means that the work done is going to be equal to the final kinetic energy, which is a half times the mass times that final speed squared, which was 5.911 squared, minus the initial, which is the half times the mass times the 4 squared. Am I going to fit this in? No, I'm not. I'm going to very quickly drag that across. And I'm going to say that that's going to multiply by the 4 squared. And hopefully I'm going to end up with 14.2. So I'm going to do the half times the 1.5 times the 5.91 squared minus a half times 1.5 times 4 squared. And we do get 14.2 joules to three significant figures. So you can either do it using energy considerations or you can do it using integration. I'm going to do this third one, and then you guys are going to have a go at this last one that we've got here. So a particle P of mass m is moving along OX in the direction of x increasing. In other words, here's O, it's just moving along the x-axis to the right. At time t, the only force acting on P is a resistance of magnitude mk brackets c squared plus v squared, where v is the speed of P and c, k are positive constants. When t equals 0, P is at O, meaning its displacement is 0, and its speed is capital U. The particle comes to rest at the point A. So I know that later on, this is at the point A, it comes to rest at this point, and we're going to try and find out what the distance is in terms of K, C, and U. Well, look, I'm interested in X and V, which means I'm going to use that A is V dV dx, okay? And this time, we've got that the force is a resistance. This is a resistance. And so we're actually talking about it moving to the right. So when I do the F equals ma, my force is going to be negative. It's going to be minus mk c squared plus v squared is equal to the mass times the acceleration, which is v dv dx. I just didn't think you don't think you'd see the day in mechanics where there's not really a single number anywhere. It's all letters, but here we are. So I'm going to cancel the m's, and then I'm going to do some integration, okay? Now, I need all of the v stuff to be on the right-hand side, so I'm going to send all of the v's onto this side because that's where dv is, and there's some v's over here. So what I'm going to do is I'll leave the k on the other side, so I'm going to have my minus k dx, and then to get this c squared plus v squared to the other side, it's going to go over there by some division like this. As usual, we put in the integration signs, and now we're just going to go about our integration. So that's minus kx. I'll do the constant on the other side. Now again, I'm not teaching about integration here, but hopefully you recognize that the numerator is related to the derivative of the denominator. The derivative of this denominator with respect to v, that's just going to differentiate to nothing. This is just going to be 2v, and this is a v here. So it's going to be an ln of this, and I'll half it to get that part on the top. So it's going to be a half ln of c squared plus v squared. Now, I am using these modular signs to say that it's positive, that it has to be positive. It's obviously going to be positive because c squared and v squared are both going to be positive, but I'm just going to keep using it anyway. And I'm going to add in a constant term. Now, I've already used c, I've already used k, so I'm just going to use a different constant. I'm either going to use capital A, that's a popular one, or you could use alpha. I'm going to just go with capital A in this case. So they all follow the same kind of pattern. I'm now going to use this information to find out what capital A is equal to. So x is equal to 0 and v equals capital U. That gives me 0 equals a half ln of c squared plus u squared plus a, which means that a is minus a half ln of c squared plus u squared. So I'm now going to take this equation that we've got here, let's put it over here, and I'm going to just solve the problem with this. I'm going to say that v is equal to 0, what is x equal to? So minus kx equals a half ln of c squared plus, I've said that v is going to be 0, so I'm just going to say c squared, half ln c squared, plus a, which is minus a half ln c squared plus u squared. Did I do all of this right? Yes, I have done. And I'm going to try and find out what x is equal to at this particular point. So I'm going to try and make x the subject of this. I'm going to juggle things around so that I have the positive x on this side, so that I end up with a half ln of c squared plus u squared minus a half ln c squared equals kx. Now I can combine these ln's into one single thing, which is going to be the ln of, I don't really need the modular signs anymore, that's c squared plus u squared over c squared equals kx. I'm also now going to divide by k so that I get x equals 1 over 2k ln of c squared plus u squared over c squared. Now, I borrowed this one from the textbook. If you want to do part B of this, there is a part B of it in the textbook. It's just the same kind of thing, to be honest, apart from instead of doing a equals dv dx, you use a equals dv dt, and it has some slightly different integration that comes along with that one instead. So if you want to have a go at that one that's in the textbook, of course, you can try that one too. Now, the one that I would like you to have a go at is this one here about a car. So when you read through this, you just need to be a bit more careful about setting up the diagram that you have to begin with so that it definitely kind of works out exactly how you'd like it to. So just pause the video and have a go at this one. Okay, a car of mass 800 kilograms travels along a straight horizontal road. The engine of the car produces a constant driving force of 2,000 newtons. At time t seconds, the speed of the car is v meters per second. I'll change that in the PDF. As the car moves, the total resistance to motion is of magnitude 400 plus 4v squared newtons, and the car starts from rest. So that means when t equals 0, v equals 0, and it wants us to come up with what v is in terms of t. Now I've put down here, you may find this useful for some integration to kind of save you doing loads of partial fractions and stuff. We can just use the formula book for this part. Okay, so as usual, I am going to set up f equals ma. I'm using v and t, so obviously I want to use that a is equal to dv dt. So my force in this case, if I'm doing acceleration going towards the right like this, it'll be this one minus this one. So it's going to be 2,000 minus 400 plus 4v squared equals the mass, which is 800, times by the acceleration, which is dv dt. So it's 2,000 minus 400 minus 4v squared equals 800 dv dt, or 1,600 minus 4v squared equals 800 dv dt. Now, I can see pretty clearly here that everything has got a factor of 4. That can divide by 4, that can divide by 4, that can divide by 4. So it's probably going to make life a bit easier if I just write it as 400 minus v squared equals 200 dv dt. Now at this stage, all of the v's need to be on this side, and then the dt stuff is going to go to the other side. So I'm going to make this as easy as possible. I'm going to hopefully just put this 400 minus v squared onto this side, so that I'm going to get over 400 minus v squared dv. Now personally I like to just have a 1 in that part, so that means I'm going to divide by the 200. Of course you can leave it with 200 and just integrate like that. I don't know why, I just always like to have that as a 1 on that part. So I'm going to have 1 over 200 dt, and I'm then going to just integrate both sides. This is where the formula book is going to come in handy, because I have 1 over a squared minus x squared, 1 over a squared minus x squared in this case. Now obviously I've put that correct part of the formula book. The more you do, the more you'll be aware of what is inside the formula book. So integrating this, I get 1 over 200t equals, using the formula book here, if you don't use the formula book, you'd have to do partial fractions, factorize this, then do partial fractions, and then integrate it, and it would then combine into this thing. But we're very lucky, we are just going to use the formula book. So in our case, a squared is 400, which means a is the square root of 400, which is 20. 20 times 20 is 400. So we get 1 over 2a, that's 1 over 40 ln of a plus x. That is a plus v, because obviously v and x are different, and 20 minus v. And then we get some kind of constant, so I'm just going to use the letter c for this. Now they told us this info, that when t is 0, v is 0. When t is 0, v is 0. So we get 0 equals 1 over 40 ln of 20 over 20 plus c. Well, 20 over 20 is 1, and ln of 1 is 0, so this whole thing is 0, so c is 0. So we have 1 over 200t equals 1 over 40 ln of 20 plus v over 20 minus v. I'm going to times both sides by 200. So when I do 1 over 40 times 200, I get 5. So t is equal to 5 ln of 20 minus v, 20 plus v over 20 minus v. And hopefully what I'm going to do is I'm going to put all of this stuff to the left so that I'll be able to do some more working out on this same page. We're going to try and make v the subject. The question wanted us to find v in terms of t. So I'm going to do t over 5 is the ln of 20 plus v over 20 minus v. And this is where I'm hopefully going to be able to continue with this way over here. So I'm going to do an exponential now. So I'm going to say that 20 plus v over 20 minus v is e to the t over 5. Then doing some multiplication up, 20 plus v is equal to, I'm going to just multiply this by this. That's going to give me a 20 e to the t over 5 minus v e to the t over 5. I'll put the v's on the same side, so that's v plus v e to the t over 5 equals 20 e to the t over 5 minus 20. Factorise this side and I get e to the t over 5 plus 1. Factorise this side and I get e to the t over 5 minus 1. I think we did an example really similar to this in kinematics. So if you were doing that video recently, you might recognise this. Very similar numbers, very similar structure. So this means that my speed is this. This is v in terms of t. And then says, show that the speed of the car cannot exceed 20 meters per second. So for part B, we talked about this one previously. If we look at these bits in the numerator and denominator, we know that e to the t over 5 minus 1 has got to be less than e to the t over 5 plus 1. Because no matter what this thing is, if you take 1 away from it, and on this side if you add 1 to it, this side has got to be bigger than this one. So when I divide everything by e to the t over 5 plus 1, obviously this would be e to the t over 5 plus 1 divided by e to the t over 5 plus 1. We've got that it's less than 1. Now, before, they put modulus signs around this in the book, and that's really just to show that some of the times this is going to be negative, but always the size of this is going to be less than 1. If we drew it as a graph, and you could put this on like Desmos or something, you see you get a graph that looks like this, where it is always between 1 and minus 1. If you didn't have those signs, it's not going to matter. Now, because I'm multiplying it by 20, if I multiply this by 20, I obviously, with the inequality, would multiply the right-hand side by 20, which means that the velocity is always less than 20 for all values of t. So the speed is always less than 20, hence it cannot exceed 20. So just looking out for some of those things, if you've done the kinematics ones, this should feel like a relatively familiar kind of process. So that is everything for exercise 5A. We are going to, in the next video, look at Newton's law of gravitation.